Another um, type of generative AI is neural style transfer. So maybe you've heard about cycle GANs or cycle consistent generative adversarial networks. So you could have a photograph like the one on the bottom and want to change it so it looks like a Monet painting, or you could have, if you're an artist, a Monet painting that you'd like to look like a photograph. And you can use generative models to do this so-called style transfer. Now, in the context of medical imaging, you could use this to enhance an MRI scan. You could make it look like it was collected on a different scanner or a better scanner, maybe if you want to harmonize data from multiple sites. Um, and just to explain how this works, style transfer or neural style transfer is extremely interesting. So what you do is you feed in the image whose style you want to change. That's the content image on the left. And you feed an image that has the style that you want, which is over on the right. And you would like to output an image, which is the one in the middle, that matches the content of the image on the left and the style of the one on the right. And it turns out that that object detecting CNN, the VGG19, has layers in it that encode the style. So it's an extremely interesting application. If you fed an image of a sports car and a painting into the VGG object detection CNN, it turns out that the style of the image is encoded in the layers, and you can pull it out using something called the Gram matrix. So let's say there's layers of the CNN that are interpreting those two pictures at the top. They have different channels. So each layer of the CNN might have different channels, different features that it has detected. And if you compute the correlations among these features, it turns out that it encodes the style. So the Gram matrix is something that you compute to represent the style. And then when the neural style transfer method is generating images, you say, we want to do gradient descent on the following penalty function. We'd like the image to look like it has the same content as before, but the mean squared difference in style between the generated image and the target is as low as possible. So this is a really quite wonderful approach. It's been adapted by Mengting Liu, Neda Jahanshad, and Ho Sung Kim to a generative adversarial model for harmonizing MRI. And you can see that style transfer is very, very important. I mean, you could basically take multi-cohort imaging data and harmonize all of it using neural style transfer. These methods are available. You can run them on your images and match their appearance to certain standard cohorts. This paper by Surabhi Sinha shows that the classification of Alzheimer's disease improves in accuracy if you do style transfer using GANs on the input images. So it's very, very valuable. One caveat is that if you want to disentangle the contrast of MR images from their content, you could also do it in a way that disentangles the geometry and the contrast. And this work by Liu-Henri Zhuo and Jerry Prince, they emphasize that when you train style transfer, you should probably train it on images of the same person scanned with different contrasts. And they emphasize that if you train it in that way, it won't disturb the geometry of the brain. I mean, you obviously don't want the image to be improved, but also, erase some of the important brain features as well. So this is another such approach for disentangled style transfer called Calamity. Another application of this is to create kinds of images that we can't currently create. So let's say we wanted to create an amyloid-sensitive PET scan using T1 weighted MRI and FLAIR. Why would you do that? Well, MRI is cheaper, and not everyone has access to a amyloid PET scanner. And an MRI-based estimate of amyloid burden could allow screening of large numbers of people. So this is work with Yanjin and Biogen. So what he found is that by training a neural style transfer model on paired MRI and PET data, where you know the answer, it could generate realistic synthetic PET data for people that hadn't had such a scan. Now, these methods work if there's some mutual information between the signals on the left and the signals on the right, and they're very attractive ways of both enhancing images and generating new contrasts that we can't